Okay, it's a great pleasure to have Professor Eric Rowell from Texas A&M University to give us a talk today. He will talk about the loop Hecke algebra and conserving Young-Baxter operators. Eric, please.
Yeah. Thanks very much for the invitation to speak. And it's great to be virtually in Beijing. I visited many times, and I wish I could go there again soon. Okay, so what I'll talk about is this. It's really parts of 3 papers. So I'll talk about this loop Hecke algebra and these charge conserving, and it's I'm trying to be very honest here, how we came to the problem of thinking about what we'll call charge conserving Yang-Baxter operators. And it kind of came because we were looking at this loop Hecke algebra. So that's the idea. So this will be joint work with Paul Martin, all of it, of Leeds University in the UK. And then 2 of the 3 papers or research projects are also with, one of them is with Celeste Damiani, and the other one that we're working on now is with Fiona Trzaskowska. So let me give a little motivation here. So when we talk about 2+1 dimensional TQFTs, one of the things that this produces for us are representations of braid groups for any surface. And so one might wonder, what do you get if you look at 3+1D TQFTs? We should get representations of something. And so what is that thing that we get? I claim that maybe one reasonable thing is representations of something called motion groups. So motion groups are a generalization of braid groups. So let me explain a little bit about that. First, let me point out that the braid group itself has many different sort of definitions. One is just an abstract definition, which is just to give it by generators and relations. And so we have n generators, or rather n-1 generators satisfying the usual braid relations. This is the standard braid relation. This is the far commutation. So that's just abstract. It also is the mapping class group of a disk minus endpoints. One way of realizing this is that you can sort of write it out by looking at its action, the action of the mapping class group on the fundamental group, which in this case, the fundamental group of this, of a punctured disk is just a free group on the appropriate number of generators. You can also kind of give a geometric definition, which is maybe the first one you would think of. And so you just think of braids as being some kinds of kind of curves in R3 or in a slab in R3 up to isotopy. So that, like, for example, these 2 braids are the same. So there's an equivalence relation. And finally, you can realize it as the motion group of something. And I'll explain what motion groups are in a moment, but this will give you an intuitive idea. So what you should think of is take those points in the disk and think of moving them around inside the disk in such a way that as a set, they come back to themselves. Okay, so it's sort of the set at the beginning and the end is the same. And so this gives you something called the motion group. And it turns out that it's the braid group for this particular configuration, points in a disk. So let me talk briefly about braid group representations. before I get into this more general thing. So we have plenty of definitions of the Braid group, so we can study the representations. And so maybe the most famous representation is the Rowell representation that he defined in 1936. And it's given by taking the generators of the Braid group and sending it to matrices that look like this. So they're sort of block diagonal. They're mostly the identity, but then there's one 2x2 square, which is interesting. Depending on the value of t, so you can take t to be a complex number, then the Rowell representation, well, it's never irreducible, but depending on t, it could have the maximal irreducible sub-representation could be dimension n-1 or n-2. It just depends on whether t is a root of unity of order n or something like this. But anyway, these are famous representations. Similarly, you can define the standard representation, which is given by sending the generators to this matrix. So this is an n-dimensional representation. Turns out this is irreducible on the nose. There's no sub-representations. So that's an interesting one as well. Another way of getting representations of the Braid group, which is maybe a little more modern, would be to try to find finite dimensional quotients of the Braid group algebra. Okay, so here K is a field. Take the group algebra. This is, of course, a huge ring, but then you might look for extra relations that make this make it so you have a finite dimensional quotient. And maybe a very famous one is the Hecke algebra, depending on a parameter t. So it's, in this case, the field is Q adjoin T, and you just mod out by the ideal, two-sided ideal generated by these relations. Okay, and lots of things are known about this. So for example, the dimension of the Hecke algebra is n factorial when t is generic anyway. And you can think of it as being kind of like a deformation of the symmetric group, because you see here, instead of having the generators have order 2, right, it satisfies a quadratic relation. So anyway, these are interesting ways of getting representations of the Braid group. And right, another way of getting representation of the Braid group is to look at the Yang-Baxter equation. So this is comes from statistical mechanics, also quite classical. So you have some vector space V, and you look at an invertible operator on V tensor V. Then you define R1 and R2 in this way, just tensor up with the identity on V. So these act on 3 copies of V. And then, well, the Yang-Baxter equation is exactly this one that says that they, right, anyway, so this is a nice equation, and it implies, so if you have a matrix that satisfies this equation, then you get representations of the Braid group on the nth tensor power of V by sending the generator to just tensor up R with the identity an appropriate number of times on each side. And sometimes this is called a braided vector space. Okay. Okay, so pretty elementary so far. Let me now introduce kind of the next dimension up idea, and that is these motion groups. So these were originally studied by Dom in his thesis at Princeton in '62, and then Goldsmith also in her thesis at Princeton, but in the '70s, and then she wrote some papers later, mostly in the '80s, early '80s. So what's going on here? So don't worry too much about the details here, but the idea is you have some submanifold. So you have M a manifold in a submanifold. So it could be, for example, a torus or a surface of genus 2, and N could be a collection of points. Or it could be the the 3-ball with some trefoil knots embedded in it. That could be your N. So a motion of N is basically just it moves around inside. It's an ambient isotopy, and so then so it's an ambient isotopy of N in M, so that it starts with the identity, so nothing, and then at the end, when t is equal to 1, n is back to n as a submanifold. So it could have moved the points, but it has to preserve it sort of set-wise, really. And then there's motions that are stationary, so sort of the boring motions, which would be where n doesn't sort of really move out of itself at all. So you can think of taking like a circle like this and just rotating it a little bit in space. That would be a stationary motion. Okay. Right. And then we say two of these motions are equivalent if one followed by the inverse of the other is a stationary motion. So that gives you an equivalence relation. And so then the motion group is the group of motions modulo this relation. Okay. I'm going to give you a nice example, and it'll be the only example I'm really going to worry about today. So this is called the Loop Braid Group. So here, our ambient space is the 3-ball, and we're taking disjoint union of unlinked circles sitting inside. So just some loops. So I don't know if you can see the video of me, but here I have a couple of rings, and we can think of them as being in the space. And there are two kinds of motions that generate the whole motion group. So one of them is simply the interchange of the two loops, okay? Which, if you want to think about it as time going upwards, then it's something like that, okay? So you sort of interchange the positions without them sort of interacting, really. The other more interesting one is where you take one and you pass it through the other one and then continue, okay? Sort of the path. So just one going under the other and out. That's another motion that's non-trivial. And it turns out that any motion of any number of circles in the 3-ball can be obtained as compositions of these. So of course, we can try to think about a presentation of this group. And it's quite interesting. So the leapfrog, this sort of taking one and passing through the other, we'll sort of think of those as being like, we'll label them like by sigmas. And then the interchange will be like s's. And then of course, for each pair, adjacent pair, you have a sigma I and an si. For the I and I plus first loops. So they satisfy some relations that one can pretty readily check by looking at what happens on the fundamental group, for example. So you get, it turns out that the leapfrogs give you, just by themselves, gives you a copy of the braid group again. The loop interchanges give you a copy of the symmetric group just by themselves. And then there's a bunch of, in fact, 3 types of mixed relations. Okay, and so one of them is just Farr commutation, which is obvious. The other ones aren't so obvious, but you can check them, that they satisfy something that looks a little bit like the braid relation, but with some s's mixed in instead. Now, it's very important that you distinguish between this L2 and another one, which you might think of, which would be sigma I plus 1, etc. This one is not satisfied. So there's there's sort of an asymmetry to this picture. Okay, so that is the loop braid group, and we'll be focusing a little bit on that one. Are there any questions? Is this clear? What's going on here?
Yes, it's clear.
Great. Okay. Okay, so now how do we get representations of the loop braid group? Well, very natural thing is just to lift representations of the braid group, since the braid group sits inside as a subgroup. It doesn't sit inside in a particularly natural way, at least in the group theoretic sense. It's not a normal subgroup, for example. And so You can't just use Clifford theory or something like this, but you could still ask the question of how to lift these things. And this has been done, certainly for the Barrow representation, for the standard representation. We know what to do. Another kind of lift would be if you have a solution to the Yang-Baxter equation, RV, then you might ask for an S, so that when you define RIs and SIs in the same way as we did before with the Yang-Baxter equation, then they satisfy all the relations. Okay, so that's a kind of lift as well, but it's a sort of slightly different or maybe more specific way. And then another approach, of course, all of this influenced by our knowledge of the Braid group itself, is you could ask about finite dimensional quotients of the group algebra of the loop braid group. Okay. Okay. So let's focus first on the last one. So this is what we did with Damiani and Martin. We considered the first thing that you might wonder is, well, what if I just throw in the Hecke relation, right? That worked great for the braid group. That gave us a finite dimensional quotient. Unfortunately, it's not finite dimensional if you just throw in that one. Okay, still infinite dimensional. And so it's not so useful for constructing finite dimensional representations. However, we were able to prove that if you throw in the Hecke relation, together with two other relations that look kind of like the Hecke, but now they're mixed, you see? There's S's and sigmas showing up. Turns out this is finite dimensional. Okay. And so, well, it's in some ways kind of luck, but in fact, we had some hint as to why these are the right relations, which I won't go into today. But it is finite dimensional, and we will call it the loop Hecke algebra and denote it in this way. Okay. Okay. Right. So it turns out that this loop Hecke algebra, we didn't really understand it too well. We could show that it's finite dimensional, but for example, we couldn't compute its dimension in general. And so we started looking for representations of the loop braid group that factor over the loop Hecke algebra to try to get some of the representations. And interestingly, we were able to find a representation that we will call sort of local. And why is it local? Well, it comes from a loop braided vector space. The specific R that works is this one. Sorry?
It's okay. I think someone just entered and forgot to unmute. Mute.
Okay. Okay. Yeah, fair enough. Okay, right. So if you take this R matrix, very specific R matrix, and then take S to be R evaluated at Q equals 1, right? So it would be like 1, 0, 1, 1, minus 1, something like that. That would be S. Turns out that this, of course, one verifies that it satisfies the loop braid group relations. And moreover, it satisfies all of these relations. And so in particular, it's a representation of the loop Hecke algebra. Okay, so that's kind of nice. We have a representation that we can get our hands on. And it's in the usual way, right? You just define the image of sigma I and SI to be the usual thing, tensor up with the identity. Turns out that at least in for low values of n, this representation can be shown to be faithful. So that's pretty amazing to have a nice faithful representation of this thing. And conjecturally, once you get up to 7, you're pretty convinced, right, that this representation should be faithful for all n. And so we should be able to study the loop Hecke algebra by studying the image of this representation, since it's a faithful representation. And we can work out a lot of things. So for example, when Q is sufficiently generic, we know exactly what the dimension is. It's 1/2 of this binomial coefficient. Okay. So that's pretty interesting, but this got us to thinking, what is so special about this particular R matrix that made it so that this was able to lift to a loop braided vector space? Why were we able to find an S? Because it seems like, at least in experiments, it seems pretty rare. There are many examples of R matrices that don't lift to loop braided vector space. So one of the things we noticed about it was its structure. And so you'll notice that this matrix, it sort of is block diagonal, and it only mixes sort of in this middle part here. And so the answer seems to be, one possible answer that makes this special is that it is charge conserving. Okay, so I'm about to define that for you. So what is a charge conserving Yang-Baxter operator? Actually, what is a charge conserving operator at all? Well, the idea is you have some vector space, V, and you have a basis, an ordered basis. And we're going to use the computer science notation for EI tensor EJ, so this standard basis of just IJ. And we're going to define a sub-vector space just to be the span of IJ and JI. Here, I and J could be equal, or they might not be equal. So it's either two-dimensional or one-dimensional. And in general, we say that an operator T on two copies of V is charge conserving if it preserves the spaces VI, J. Okay. And since we're going to be looking at automorphisms, this will actually be equal. But just in general, this is the definition. So when V is two-dimensional, this is just exactly saying that the matrix has this form in that basis, in the standard basis that you might construct for two copies of V. Okay, so that's what charge conserving is. You can well imagine what it would mean to be charge conserving on many copies of V. It's quite similar. Okay, anybody have any questions? Is it clear what charge conserving is?
Yeah.
Good. So let me show you what charge conserving matrices look like for three-dimensional vector spaces, just to show that there's something more to it. So here for V of dimension 3, this is what it looks like, where the blank spaces are all zeros. Okay. And so you can kind of see that there's a bit of, there's some interesting mixing going on, right? So there's a 2x2 matrix, there's a 2x2 matrix, there's another 2x2 matrix, and then there's some diagonal pieces. That's how all these spaces show up. So the general form for any charge conserving operator will be, well, just take T, when you restrict it to Vij, we'll call that Aij. This is for I less than J, you might as well choose. And then for the one-dimensional spaces, we'll just call that scalar AI. So in general, you can encode any charge conserving operator on two copies of a vector space, just as a sequence of n scalars and n choose two 2x2 matrices. Okay. And so if you wanted to work it out, if you wanted to try to understand this problem, then you need to determine this many scalars to solve this. Okay. And that's the question that we decided to think about. We wanted to classify all, if possible, charge conserving Yang-Baxter operators up to appropriate symmetries. Now, I don't know if any of you have tried to solve the Yang-Baxter operator. It's a pretty hard question, actually. So the current status of general Yang-Baxter operators is that we know how to classify them. We know complete solutions for n equals 2. So the dimension of V to be equal to 2. For 3, it's already a wide open question. So it's a pretty hard question to classify all Yang-Baxter operators. But see here, we're giving ourselves a little advantage by requiring them to be charge conserving. Okay. So the symmetries help quite a lot. So it turns out that if you have a charge conserving Yang-Baxter operator, then you can conjugate it by a tensor product of some permutation matrix, and it will remain charge conserving and a Yang-Baxter operator. It's also the case that if you conjugate it by any diagonal matrix, it remains a charge conserving Yang-Baxter operator. And it's also the case that if you apply the flip operator, this will preserve this. Now, I should remark, in general, we know that if you have a solution to the Yang-Baxter equation, and you conjugate by Q tensor Q for any invertible matrix Q, it's still a solution. However, it will generally destroy the charge conserving property. So we don't allow that as a symmetry. On the other hand, if you take a general Yang-Baxter operator and try to conjugate by a diagonal matrix, it won't be a Yang-Baxter operator anymore. So this is a special symmetry that charge conserving Yang-Baxter operators have. So they have both more and less symmetries in some sense. Okay, and then the P, we don't, it's interesting, but we don't use it so much. But in any case, we're able to give a complete solution for n equals 2. Not too surprising. They look like this. There's sort of 4 types. They're either just diagonal or scalar multiples of the identity. They're these ones that are sort of symmetric here. And then there's these more interesting ones, okay, where the sort of this middle piece here is non-trivial. It will always have 1, 0, either upper left or lower right. So you just calculate from general form. It's an easy calculation to do. So that's n equals 2. And well, you can imagine what we did. We continued this idea. And turns out we discovered a pretty interesting combinatorial description of all solutions. We can completely describe them up to these symmetries I've mentioned. So this is going to look a little bit like, for the moment, you'll be like, what does this have to do with the braid group or Yang-Baxter operators or anything? But let me give you a combinatorial device that we'll use to describe all solutions. So here's what we do. We start with a set of n things, 1 through n, which we'll call individuals, like people, okay? The first thing we're going to do is we're going to partition this collection of people into k nations, okay? So we divide all the people into nations, and we're going to do it just to avoid extra sort of ambiguity. So we have k nations, so n1 through nk, and turns out we can require that when you partition it, it respects the order. In other words, individual 1 is in nation 1, individual 2, if nation 1 has more than one person, is also in nation 1, etc. So nation 1 has the first bunch of people, and then of course the last person, individual n, is in the last of the nations. Okay. Then we're going to further break the nations into counties, okay, or if you prefer states, or maybe you prefer provinces. But anyway, it's a way of breaking up countries into people, yeah, people into in a given country into smaller subsets. And so each nation in I will be the disjoint union of these counties, Cij. There'll be some number of them for each I. Again, respect the order, okay? And then we're going to do one more thing, which we often do here in the States, is we color counties either blue or red. So each county is going to get a color. Okay, so here it has to do with your political persuasion, whether it's blue or red. And we're going to make one extra stipulation, again, to avoid extra ambiguity. The first county in any nation is always red. Okay, so that breaks some symmetry that we don't want. So this looks a bit complicated, but it turns out that you can just describe it very easily using something called bicolored composition tableau, which are kind of like Young tableau, but they don't have to be top and left justified. They don't have to, sort of live in a corner. They can sort of be a bit different. So I'll give you an example. In this case, I have n is 11. So I have 11 individuals, and each nation you can think of as being one of these things. So this would be a nation. So I'll put that. We have 4 nations here. And then each nation is broken into counties. So this one here would be like C11, C12, C13. So nation 1 is broken into 3 counties. Nation 2, right? So this would be C21, C22, C31, C32, and this is just C41. Okay, so those are the counties. And then we color the first one red automatically. And then we're free to color the rest of them either color, doesn't matter. Okay, so you can already think about, well, how many ways can you do this? And we'll discuss this in a moment. But the point is that from this, if you give me a bicolored composition tableau, as I've done, or if you've given me this sort of colored counties within nations choice, then I can give you a charge conserving solution to the Yang-Baxter equation. And this is how I do it. So all I need to do is I need to tell you what these 2x2 matrices are. There's n choose 2 of them. And I need to tell you what these scalars are. So if individual I lives in county SX, then AI, so this sort of 1-by-1 submatrix, will be either alpha S or BS, depending on the color of the county. Okay. So the S sort of corresponds to the nation. And so, I'll sort of add this in. I got it below, but there's some stipulations. Alpha S is non-zero, beta S is non-zero, alpha S plus beta S is non-zero. So they're scalars. Okay. Now I'm going to tell you how to describe the 2x2 matrices. So again, we're picking I less than J, as we may. If I and J are in distinct nations, then Aij has this form. So here, this is mu st. And so for each pair of nations, there's a new scalar, mu st, and I use it for that pair. Okay. But it's the same st. Notice it doesn't depend on I and J. It only depends on which nations I and J live in. Okay. Now, if I and J live in the same nation, but distinct counties, okay, so let's see, there's a little typo here. That should be OI. Okay, so if they live in distinct counties in the same nation, that's when you get this interesting one. So this is what you will assign for that matrix here. Alpha S plus beta S minus beta S, alpha S. And again, these conditions I've already given you. So for each nation, you have 2 new variables, at least if the nation has more than 1 county. Okay. And then finally, suppose that I and j actually live in the exact same county. Well, then it's this diagonal or scalar multiple of the identity, gamma, gamma. And here gamma takes on two possible values, depending on the color of the county SX. It's either alpha S or beta S, depending on if it's red or blue. So notice it's exactly the same as this scalar here. Okay. So this is a construction. And so the theorem is that, first of all, this gives a solution. One can verify this. Takes some work, and there's some pretty deep lemmas, but it can be done. Moreover, up to the symmetries I've described, meaning I'm allowed to conjugate by tensor squares of permutation matrices. So I'm sort of allowed to make a local change of basis, local permutation of basis. I'm also allowed to conjugate by diagonal matrices. Up to those symmetries, this gives you all solutions. Every charge-conserving Yang-Baxter operator can be changed into one of these solutions by means of these two symmetries, either permuting the local basis and or conjugating by a diagonal matrix overall. Okay. And moreover, up to changing the variables, that's sort of a thing one can do, and permuting nations, permuting individuals within nations, these are sort of unimportant things. This actually forms a transversal, meaning that these are essentially distinct solutions. There's no overlap. So a given bicolored composition tableau, two distinct ones will give different solutions. Up to potentially, like maybe they're the same once after changing variables or something like this for some bad reason, but typically they'll be different. Okay. Okay. So it's a complete solution to this situation. Okay. Now, you might wonder how many solutions there are, or rather how many orbits of solutions, because of course we're looking at it up to a kind of symmetry. And it turns out that we can count. So the way we count is we first look at all of the situations where all individuals are in a single nation. And you count how many you can construct in this way. And that turns out to be a power of 3. And then you do something called the Euler transform, which is a well-known combinatorial construction that is sort of like when you have multi-sets, because that's sort of what we have. So it's sort of converting sort of local information, and then you have multi-sets of these things. The right thing to do is, according to the combinatorialists, is use the Euler transform, and you can count. And so in this case, for various values of n, so n equals 1, of course, there's only one solution. For n equals 2, we already saw there are 4 solutions. We wrote them down, 4 orbits of solutions. And for 3, it's 13, 4, it's 46, and it goes on like this. Okay. Now, let me give you a little bit of a clue as to how we do this. So there's another more geometric encoding of these charge-conserving operators, and that is you use them to label directed in simplices. Okay, so you'll notice that when I gave this, right, so like this picture here, look, there are n of these single sort of 1-by-1 guys, and there are n choose 2 of these 2-by-2 matrices. So we take the n simplex, it's directed, we label the vertices 1 through n, and then we attach one of these scalars to each of the vertices. And then for the edges, we label them with these 2x2 matrices, A, I, J, where I is less than J. And so that's why you need the direction. Okay. And then it turns out that one can show that, so the edges are labeled by 2x2 matrices, the vertices by 1x1 matrices. It turns out that the constraints that you get from the Yang-Baxter equation kind of live on triangles in the sense that they involve up to 3 indices. And this turned out to be quite valuable in our approach to doing this. Okay. So is it clear how we do this? So we sort of have, you sort of just give me like, you know, some pictures, some boxes like this stacked on each other, sort of each nation, and then the counties go this way. You put your individuals in the boxes, and then you color them according to this rule. Once you've done that, you can even just program a computer to spit out this sequence here. And this sequence here obviously determines a charge conserving operator, but in fact, it satisfies the Yang-Baxter equation as well. Okay. So we have a complete solution to this. And in some ways, this is kind of one of the first situations where we have a classification of all solutions to the Yang-Baxter equation all in one, sort of in a family for all dimensions. There are a few other cases that maybe it could be argued also works like this, like the Gaussian solutions. But anyway, this is sort of what came out of this project. Okay. Now, of course, the original question you may have forgotten by now. So we were really looking for solution, or rather representations of the loop braid group. And we had one example of something that was a charge conserving Yang-Baxter operator that lifted. And so you might wonder, well, do they all lift, right? Well, the answer is no, unfortunately, they don't all lift. I can give you a quick example of one that doesn't lift. If I scroll back here a little bit, if you don't mind. So if you remember this original solution here that did lift, if you were to change this minus into a plus, you would still get a solution to the Yang-Baxter equation. It would still be charge conserving, but it would never lift to the loop braid group. Okay. It turns out that this one comes from a quantum group. It comes from UQSL11. Maybe this is the notation. So it's the, right, it's a supergroup. If you were to remove this sign, then it would be the one that comes from UQSL2, more familiar one. That one won't lift. So there's some more work to be done. So let's look at that. So when do they lift? Oops, too far here. Well, we recently proved a theorem that they lift if and only if this corresponding bicolored composition tableau, right, has at most 2 rows, and whenever there's more than 1 row, they need to be different colors. Okay, so things like, so 2 rows, right, something like that. That would be fine as long as the colors like, and again, this one has to be red, but I can't choose the second one to be red. It has to be blue. So this one will be a yes. But if I were to do the same thing with the same picture, but then color it all red, then this would be a big no. Okay. And that's it. We can even describe what to do. The idea is now, of course, we want to define another charge conserving Yang-Baxter operator, but with an extra special condition that its square should be the identity. And then also it has to satisfy all the various relations of the Loop Braid group. And so it turns out that what you need is for each nation, you will need to add a sign. Each nation has a sign now. And each pair of nations, there's one more variable that shows up. And the sort of the S part of the loop braid vector space, the Bij, have the form like this, where X is either plus or minus 1 or this new variable, depending on the citizenship of I and J. And then the first ones are plus or minus 1s, and there's some prescribed thing. So there's some details that I'm not giving you, but we know exactly how to describe all of these solutions. So let me just go back again briefly and point out, just so you can look at these relations again, because I went kind of fast through. So notice, this is what we're after. So we want something that satisfies the Yang-Baxter equation. These two will be satisfied. The second thing should satisfy the Yang-Baxter equation. These two will be satisfied. It should also square to the identity, the second one. This one will be for free. So really, we're checking these two. Okay, that gives you a bunch of extra constraints. And the input, of course, is our theorem that classifies all of the Yang-Baxter operators that are charge conserving, and then uses these relations to sort out what S can be extra constraints. And that's how it works. Okay, continue here. Okay. And right. And so that's all I wanted to tell you about it. So thanks for listening. And I'm happy to take questions.
Thank you, Eric. Very nice. Very nice talk. Are there any questions? Let me stop recording.